Can you see my screen?
Yes.
Yeah, very good. Okay, so yes, so thank you very much for the invitation to give a talk. And the title of my talk, as mentioned, is the reconstruction problem for D-cluster tilting subcategories of exact categories. It's based on a preprint, which you can find on the archive with the following code. You can also download these slides later, I was told. You can find them on the webpage if you want to read more carefully. So let me just immediately start with what I mean by the reconstruction problem. So it asks, let's say you are given an exact category and you're given a D-cluster tilting object inside that exact category. Then the question is, can we determine the exact category from the endomorphism ring of the D-cluster tilting object? If we know the isomorphism class of the D-cluster tilting object, can we determine the exact category up to equivalence? If you don't know what an exact category is, or if you don't know what D-cluster tilting is, don't worry, I will introduce that very soon. And for those of you who know what a D-cluster tilting object is, or an exact category is, the next part might be known or familiar. So then I suggest you maybe instead think about this problem. Do you think it's true? Do you think it's false? And if it's false, is there some way of modifying it to make it true? For me, this will be the motivating problem that I will use to introduce the main results from my paper. So let me start with a plan of the talk. First, I will say something about the background, like what is an exact category, what is a D-cluster tilting subcategory. And then I will go back to this reconstruction problem and use it as a way to introduce the main results from my paper. And then in the last part of the talk, I will say something about how these main results are proven. So what ingredients go into the proof. Okay, so let me just immediately start with the background. So I want to tell you what an exact category is, and I want to tell you what a D-cluster tilting subcategory is. I want to start with exact categories, and an exact category is a particular example of what's called a conflation category. So I'll just tell you first what I mean by a conflation category. So a conflation category is a pair where you have an additive category E and you have a class S of kernel co-kernel pairs in E. So in other words, S is a subclass of the class of all composable morphisms Fg, such that F is a kernel of G, the first morphism is a kernel of the second one, and the second morphism is a co-kernel of the first one. So that's what I mean by a kernel co-kernel pair, and we fix a class of kernel co-kernel pairs, so a subclass in here. And we assume it is closed on isomorphisms. So a conflation category is something very simple. It's just an additive category where you point to a specific class of kernel co-kernel pairs that you somehow keep in, that you remember. If you have an abelian category, of course, a kernel co-kernel pair is the same as a short exact sequence. In general, we call the elements, these kernel co-kernel pairs we care about, we will call them conflations. So we have an additive category together with a class of conflations. And the main point is somehow that you don't introduce any additional properties on the additive category, but you add an additional structure, and this structure is this class S. So whenever you introduce, give new constructions based on a conflation category, or talk about functors between conflations categories and so on, you need to take into account this additional structure. Okay, so I want to talk about conflation categories because I want to talk about exact categories. So exact categories is a particular kind of conflation categories. And the idea is that you want to inherit the conflations from abelian categories. So let me immediately tell you what this means. So an exact category is a conflation category, so an additive category together with a class of conflations S, such that first the additive category is equivalent to what's called an full extension closed subcategory of an abelian category. There exists an abelian such that E is a full extension closed subcategory of A. So this tells you something about E. Then I want to say something about S, and that is that the kernel co-kernel pairs in S, the conflations are precisely the complexes, the three-term complexes in E, which are sent to short exact sequences in A. So here I said extension closure, and I should quickly tell you what that means. So a subcategory is extension closed if you have a short exact sequence in your ambient category, in your abelian category A, and the two outer terms A1 and A3 are in the subcategory, so A1 here and A3 here, then the middle term A2 has to be in the subcategory. So we see that S consists of the complexes in E, which are short exact sequences in A. And this is what I mean by inheriting the conflations from short exact sequences in abelian categories. And the fact that the extension closure tells you that they're inherited in a nice way. You might have seen a different definition of exact categories by giving a list of axioms, so-called the Quillen axioms. Now we can show that that definition is equivalent to this one. But for me, this is a bit more conceptually easy to understand what we have. So I prefer this one rather than the axiomatic definition. But we will get back to the axiomatic definition later. I will typically not write S in this class of conflation to S and simply write E for the exact category ES in case you see that later. I say an exact category E, but then I of course need to remember that I have an underlying class. So one advantage with exact categories is that you can do homological algebra there. So as you probably know from some course in homological algebra, you can do homological algebra in an abelian category. You can talk about projective objects, injective objects, short exact sequence, long exact sequences, X groups, derived categories, and so on. And because the conflations in S are inherited from an abelian category in a nice way, it turns out we can also do homological algebra in the exact category, but then relative just to those conflations. So in similar way, you can define projective and injective objects, higher X groups, derived categories, and so on for exact categories. In particular, we can define long exact sequences. And just to illustrate how this works, I just want to tell you what a long exact sequence in an exact category is. So it is a complex. So the composite of any two morphisms is 0. And normally you will require it to be acyclic. So the image of one morphism should be the kernel of the consecutive one. For an exact category, you have to be a bit more careful, but it can be, exactness can be defined in the following way, namely that this complex is now namely that you have objects fi minus 1, fi plus 1, fi plus 2. You have morphisms as indicated by the dashed arrows, such that first each triangle, this triangle, the triangle ei minus 1, fi ei, the triangle ei fi plus 1, ei plus 1, all of those triangles commute. And secondly, each diagonal is a conflation. So it's one of these kernel co-kernel pairs that lies in S. So we see from this that this morphism ei minus 1 to ei is the composite of the morphism from fi to fi and the morphism from fi to ei. And then similarly for each triangle. So this tells you that this complex is somehow glued up by these conflations here. So that's what we mean by a long exact sequence in an exact category. Next, I want to tell you what D-cluster tilting is, what a D-cluster tilting subcategory is. So D-cluster tilting is defined for any positive integer D. So we fix such an integer D and an exact category E. Then we have the following definition due to Yama from 2006, says that a full subcategory of an exact category E is D-cluster tilting if it satisfies 3 conditions. The first condition is that it's rigid in degrees between 0 and D. So there are no extensions for any 2m in our subcategory. They have no extensions in degree 1, 2, up to D-1. So xi, e, m prime is 0. And here this X group is of course defined relative to the exact structure in E. The second condition tells you in some way that M is big enough and that it generates and co-generates E in a nice way. And this is phrased in the following way. So for any object E in our exact category, you can resolve E by objects in M in D steps. And by that, I mean that we can find an exact sequence, that's in the top one here, where E is on the rightmost side and all the other objects are in our subcategory. And then you also have the dual condition. E can be co-resolved by objects in our subcategory in these steps. E is on the leftmost side, and then all the other objects are in our subcategory, and you have an exact sequence. Again, exactness is defined as I mentioned on the previous slide. And then the last condition is just a bit technical one, which requires M to be closed under finite direct sums and summons. And you could probably skip finite direct sums here, and it would be enough to say summons. So an object is D-cluster tilting if, so now we define this, what it means for a subcategory to be D-cluster tilting. Now an object is D-cluster tilting if its additive closure is a D-cluster tilting subcategory of E. So here add M is just a smaller subcategory of E containing M, which is closed under finite direct sums and summands. So I think a lot of you have seen a definition of D-cluster tilting before, but you might have seen a different definition, which was phrased in terms of rigidity, that you have no extensions, this is the same, but then also a maximality property with respect to rigidity, that if you have any object in E which has no extensions with M in degrees between 0 and D on one side, then that object had to be in M to begin with. One can show that that definition is equivalent to this one. I prefer this one a bit over the other one. To me, this is a bit more clear what's actually going on. You have a subcategory which generates and co-generates your ambient category in a nice way together with rigidity. So note that if you have one cluster tilting, a one cluster tilting subcategory of E, it's basically just the same as having the entire category. As I mentioned, you can define D-cluster tilting for any positive integer, in particular for D equals to 1. For D equals to 1, this first condition becomes empty. There are no integers between 0 and 1. And the second condition just tells you that for any object E, there is an exact sequence 0, M, 1, E, 0. In other words, any object E is isomorphic to an object in M, and therefore has to be in M. So one cluster tilting is just the same as having the whole category. So in particular, having a one cluster tilting object, as we defined here, is just the same as having an additive generator of the category. So if you have a way of talking about indecomposable objects, say you have a Kroll-Schmidt category, then having a one cluster tilting object is just the same as saying you are a finite representation type. You have finitely many isomorphism classes of indecomposable objects in E. So in this way, D-cluster tilting objects generalize in some sense this notion of representation finiteness. So why do we care about D-cluster tilting subcategories? Well, I would say one of the main motivations is that they occur in many different contexts. So ideas in higher Auslander-Ruyten theory and D-cluster tilting were used in the recent proof of the Donovan-Weems conjecture by Hasso, Keller, and Muro. They also occur when you study partially wrapped Fukaya categories. So partially wrapped Fukaya categories of certain symmetric products of disks are equivalent to derived categories of certain of what's called higher Auslander algebras. And higher Auslander algebras are algebras that naturally occur when you study the property of D-cluster tilting and this higher Auslander Ritten theory. If you have a D-cluster tilting subcategory in a module category of a finite dimensional algebra, then you can use that to generate and obtain tilting complexes. And this is via functorially finite higher torsion classes. So this is some kind of generalization of the classical bijection between functorially finite torsion classes and two-term tilting complexes. This is a higher version, and you get some kind of tool if you have a D-cluster tilting subcategory to generate tilting complexes, and therefore to generate some kind of derived equivalence to certain TG algebras. So this is a work in progress I have with some co-authors. Then if you care about NCCRs of isolated singularities, then that's closely related to two-cluster tilting modules. In fact, Gorenstein, so maximum Cohen-Macaulay NCCRs precisely correspond to two-cluster tilting objects in the category of maximum Cohen-Macaulay modules. They also occur in the higher dimensional Mackay correspondence. Instead of looking in the classic one, you look at the category of maximal Cohen-Macaulay modules over some commutative ring. In the higher version, you now need to look at the D-cluster tilting object in some in the category of maximal Cohen-Macaulay modules over some commutative ring. Then if you care about cluster categories, then whenever you have a Frobenius exact enhancement of a cluster category, you automatically get a two-cluster tilting object. So, and these are many different examples of situations where D-cluster tilting and this notion of higher Auslander Ritten theory occurs in representation theory and in algebra. A lot of people have studied D-cluster tilting for module categories of Artin algebras or finite dimensional algebras. But to be able to cover all these kind of examples, you do need to work in this kind of more general setting of exact categories. You do need to look at D-cluster tilting in exact categories. So in fact, all these examples marked in red, you have D-cluster tilting in an exact category, but you don't have D-cluster tilting in a module category, in some abelian category. So I want to just illustrate that as some kind of motivation why I'm working in this more general setting. Okay, so we've introduced much of the background, what is an exact category and what is a D-cluster tilting category. And now I want to go on and talk a bit about the main results. So let's go back to this question asked in the beginning of the talk. Can we recover an exact category from the endomorphism ring of a D-cluster tilting object? And probably if you thought about this for a bit, you realize that this should probably not be true, and that's the case. As stated, this question has a negative answer. And it's quite easy to find a counterexample. So if you have a object n, then it will always be D-cluster tilting in its additive closure when you consider the additive closure as an exact category with the split exact structure. In other words, as an exact category where the conflations are split short exact sequences. Because these conflations are only split short exact sequences, all the X group will automatically vanish, and then it becomes automatically D-cluster tilting in the additive closure. But of course, in general, E, our ambient exact category, will not be equal to this additive closure. So the endomorphism ring of M is not able to distinguish the additive closure from the exact category E. Of course, the issue here with this question is that an exact category is not just any additive category. It's an additive category endowed with an additional structure. So somehow to be able to recover that from M, we need to also endow M with an additional structure. So we need additional structure. And luckily there is such a structure that exists in the literature. And this is due to a definition and a theorem by Gustavo Hasso from 2016. So he introduces the notion of a D-exact category. So a D-exact category is an additive category together with an additional structure, which I will get back to what that is later, in the same way as an exact category is an additive category with additional structure. So what he does is he introduces this notion of a D-exact category, and he shows that any D-cluster tilting subcategory of a weakly idempotent complete exact category is a D-exact category. I will get back to very soon what weakly idempotent complete means. I just want to mention that the theorem, as stated in his paper without weakly idempotent complete, is not completely true. It's possible to make it true, but you need to modify a bit how you define the exact category. So that's why I add this assumption here. But it is a very weak assumption, and most categories we're interested in will satisfy it. And it turns out that this is sufficient to have a positive answer to the reconstruction problem. If we endow the D-cluster tilting object with such the structure coming from being a D-exact category, you do get a way of reconstructing E. So more precisely, this is the main theorem of my paper. It says that any weakly idempotent complete D-exact category is D-cluster tilting in a unique exact category. And that uniqueness is up to exact equivalence, i.e. equivalence of the underlying additive categories that preserves and reflects conflations. So I've had this adjective weakly idempotent complete pop up a couple of times, so I should tell you what that is. So weakly idempotent complete just means that all split epimorphisms in your category have kernels, or equivalent, and you can show that's equivalent to requiring all split monomorphisms in your category to have co-kernels. In particular, any idempotent complete additive category, so any additive category with idempotent split, will automatically be weakly idempotent complete. And that's also part of the reason for the name weakly idempotent complete. So this is not a very strong assumption, but for technical reasons it needs to be, we need to assume it. Okay, so now now we have a positive answer to this reconstruction problem, but then besides this kind of conceptual explanation and positive answer, why would one care about this result? So why do we care about the D-exact categories being D-cluster tilting? And for me, another motivation is the fact that it's often easier to find D-exact categories in the nature than finding D-cluster tilting subcategories. So in fact, there exist some papers where people have been able to construct new D-exact categories, but without actually being able to show their D-cluster tilting subcategories. Now, of course, you can combine it with my theorem to conclude that there exists some D-cluster tilting subcategory from them, but this one is not known before. And this is basically because in many situations it's easier to actually check D-exactness than finding an ambient exact category containing it as D-cluster tilting. So let me give two examples of this. One is the recent preprint of Carlo Klaprow from 2024, where he shows that any additive category has a maximal D-exact structure. So this is a generalization of a result by Wolfgang Rump, which states that any additive category has a maximal exact structure, no D, but he generalizes this to higher Ausland algebra, to higher Ausland theory, to D-exact categories. So then you can combine that with my result to get that any weakly idempotent complete additive category can be considered as a D-cluster tilting subcategory in an exact category in a way that takes into account as much of the D-exact structure that you can consider. And then there's another result, another paper by Hafezi, Asadullahi and Zhang from 2025, where they look at D-cluster tilting subcategories of module categories. They look at the XD functor, and they look at subfunctors with certain properties of XD functors. And then from these subfunctors, they obtained new D-exact structures on this category. Again, combining it on new D-exact categories. And then again, combining it with my results, you then get new ways of, you get new examples of D cluster tilting subcategories. Okay, so we have now given a positive answer to the reconstruction problem, and I've told you the main result relating D-exact categories to D cluster tilting subcategories, but I haven't yet told you what a D-exact category is, and that's the next step of my talk. What is a D-exact category? So the idea is that the definition generalizes the axiomatic definition of exact categories. So I will start by recalling the axiomatic definition or characterization of exact categories, and then afterwards go on and define the higher versions, the D-exact categories. For this axiomatic characterization, I first need to recall the notion of inflation and deflation. So fix a conflation category E, so an additive category, together with a class of kernel co-kernel pairs that we are pointing to, that we have fixed. Then we say that the morphism in our additive category is an inflation if it's the leftmost part of a conflation, or in other words, if it's the leftmost part of a kernel co-kernel pair in our class. And it's a deflation if it's the rightmost part of a kernel co-kernel pair in our class. So if it's the co-kernel of some kernel co-kernel pair in our class, if it's the rightmost part of a conflation. So we have the notion of inflation and deflation, and we can use that to define exact categories. Since normally this theorem that I'm stating would be the definition, would be a definition, but since I've already given a definition of exact categories, I'm kind of forced to state this as a theorem. Normally things would be done in the other way around. What I'm going to state would be the definition of exact categories, and then the theorem would be this definition I gave earlier. That would be, that you can, any exact category is an extension closed subcategory of an abelian category. But I've turned things around. Of course, you can think of the theorem as just saying those two characterizations are the same. So a conflation category is called an exact category if it satisfies some axioms. The first axiom is just that the trivial kernel co-kernel pair is a conflation, is in this class S. The second condition is that inflations and deflations are close to the compositions. In other words, if you have two inflations and you compose them together, you get another inflation. If you have two deflations, you compose them together, you get another deflation. And then the third axiom is a bit more technical to state. It says that whenever you have a conflation and you have a morphism starting in the first object in your conflation, so here you have G from E1 to F1, and you have a conflation with the inflation F. Then you can find a commutative diagram. Here F is the F in the conflation, is the associated inflation. G here is this vertical morphism. And what we're saying is that we can find F2 and H and K such that this diagram commutes, and such that the associated sequence is a conflation. The associated sequence sending E1 to E2 plus F1 via F and G, and then sending E2 plus F1 to F2 via H and minus K. This is a conflation. In particular, since it's a conflation, it's a kernel co-kernel pair. And this being a kernel co-kernel pair is the same as saying that this is a pullback and a push-out square, or equivalently a bicartesian square. But of course, this axiom is even a bit stronger since this kernel co-kernel pair is required to be an S. And then you also have the dual of axiom number 3. So it turns out that with these axioms, you can show that this conflation category is actually or this exact category is actually an extension closed subcategory of an abelian category. And this is called the Gabriel-Quillen embedding theorem, or which is what I've stated at the top, the name of the theorem. So the idea in defining the exact category is to use the same characterization as here, but we replace each conflation by longer exact sequences. So I will then first tell you what I mean by longer exact sequences, and then I will give this definition of the exact categories. So let C be an additive category. Then a D exact sequence in C is a complex. Now with D plus 2 objects or D plus 1 morphisms as a complex in C, and such that when you apply the covariant Hom functor, you get an exact sequence. So you get exactness everywhere except at the last term. So the morphism from xc xd to c x xd plus 1 is not necessarily an epimorphism, but you have exactness everywhere else. And then also when applying the contravariant Hom functor, you get exactness everywhere except you might not have an epimorphism at the end. So this should of course hold for any object in C. So if D is equal to 1, then this first condition is just saying that x0, the morphism x0 to x1 is the kernel of the morphism from x1 to x2. The second condition is just saying that the morphism from x1 to x2 is a co-kernel of the morphism from x0 to x1. So we know what the D exact sequence is, and then in the same way as an exact category is a particular example of a conflation category, a D exact category should be an example of a deconflation category. So let me tell you what that means. So a deconflation category, Cx, is given by an additive category C and a class of D exact sequences, and here D exactness is this definition is as in this definition above. And there's a D exact sequences in C, which is closed, and here I assume under homotopy equivalence. So it's simply just an additive category where you point to a fixed class of the exact sequences, and they're required to be closed on a homotopy equivalence. Note that I don't think the notion of deconflation category exists in the literature, and I'm also not advocating or saying that one should study deconflation categories in general. I just, from my purpose, it helps to introduce them before introducing the exact categories. But what I'm really interested in is the exact categories, not deconflation categories. Another note is that one-conflation categories are not actually the same as conflation categories, because requiring closure on the homotopy equivalence is stronger than require closure on the isomorphism. Of course, this won't really matter for this talk, because what I care about is the exact categories and not the conflation categories, and there the notions coincide. So for conflation categories, the sequences are called conflations. For deconflation categories, we call them admissible D-exact sequences. So now we are ready, or almost ready, to define the exact categories. First, I just want to tell you what is the analog of inflations and deflations. And you would probably come up with the same definition as I give here, if you were to think a bit about it. So we say that a morphism in a deconflation category is a admissible monomorphism, which is the higher analog of an inflation, if it is the leftmost part, so here you have F, in some D-exact sequence in X. In other words, it's the leftmost part in an admissible D-exact sequence. And dually, you have an admissible epimorphism if it's the rightmost part in an admissible D-exact sequence, if it is the rightmost part in a D-exact sequence contained in X. So now we have all the notions and terminology we need to define the exact categories. Remember, we wanted to give a higher, we generalize the definition of the exact category, or the characterization of the exact categories, to higher Ds. So we base it on this characterization. And then we get the following definition. A deconflation category is a D exact category if and only if, and then instead of having a short exact sequence in S, you now require to have the trivial D plus 1 and the trivial D exact sequence to be an X. The D exact sequence consisting just of zeros should be required to be an X. The higher analog of 2 is also quite easy to guess. You just replace inflations by admissible monomorphisms and deflations by admissible epimorphisms. Require the composite of 2 admissible monomorphisms to be admissible monomorphisms, and dually for the admissible epimorphisms. And then the third axiom is maybe a bit more complicated. So now instead of starting with a conflation, we start with an admissible D exact sequence, and we start with a morphism E0 to F0. So morphism starting in the first object in this admissible D exact sequence. So then instead of having a commutative diagram, you now require to have a morphism of complexes. Note that the top part of this, the top complex here, is obtained from the admissible D exact sequence just by removing the last term ED plus 1. F0 at the bottom here and this vertical morphism is just this morphism we are given. And then what we are saying is that there exists F1, Fd, and a complex as below, and a morphism of complexes as denoted here. And then we require the cone of this morphism to be an admissible D exact sequence. The cone of this morphism to be a D exact sequence, which is in our distinguished class. And then you also have the dual of 3, which I will leave, which I will not write down. Note that D equals 1 will recover the notion of exact categories. So that's from how I define things, it should be clear. And similar as for exact categories, for D exact categories, I will usually omit this class X of admissible D exact sequences and just write C for the pair CX. But of course, you should remember that we still have a fixed class of D exact sequences that we care about. So now let's go back to these theorems. So the theorem by Hasso states that if you have a weakly idempotent complete exact category and a D cluster tilting subcategory of E, then we get a D exact category. And now I can tell you what are the admissible D exact sequences in this D exact category. And that's namely given by the following. So MX is a D exact category where X consists of all the complexes in M of the correct length, no? D plus 2 objects, or D plus 1 morphisms, which when you send them to the ambient exact category, they become exact under the exact structure of E. So with this structure, you get the D exact category. Note that if you didn't have weakly idempotent complete, then this would not give you a D exact category. The main issue being that exactness of complexes is not preserved under homotopy equivalence if you don't assume weakly idempotent complete. So there is a way without weakly idempotent complete to get the D exact category, but then you need to close this class under homotopy equivalence. So yes, so I will assume weakly idempotent complete in my statements. Then I get the following theorem. If you have a weakly idempotent complete D exact category, then there exists a weakly idempotent complete exact category and a D cluster tilting subcategory of that weakly idempotent complete exact category, such that this D cluster tilting subcategory is equivalent to our M that we start with. And that equivalence is not just an equivalence of additive category, but it's an equivalence of D exact categories, meaning it preserves and reflects admissible D exact sequences, or equivalently it has an inverse which also preserves D exact sequences, or quasi-inverse, sorry. Yes, so here N being a D cluster tilting subcategory of a weakly idempotent complete exact category becomes a D exact category via this theorem by Hasso. And that's the D exact category I'm considering when I'm saying they're equivalent as D exact categories. The second part of the theorem is that this ambient exact category E containing N is unique up to exact equivalence. And it's not only E that's unique, but the pair En is unique. Meaning that if you had any other pair E prime N prime satisfying this condition, then you would have an exact equivalence between E and E prime, which restricts to an equivalence between N and N prime. So let's go on to the ideas of the proof. So let's start with the uniqueness. So remember, we have this theorem that I presented to you, and it somehow has two parts. It talks about the existence of a D-cluster tilting subcategory in an exact category, and it talks about the uniqueness of the exact category. So I will first say something about the uniqueness and then afterwards go on to the existence. So uniqueness follows from the fact that the inclusion of a D-cluster tilting subcategory into its ambient exact category satisfy a universal property. And it's a universal property with respect to a certain class of functors, which I will now introduce. And those functors I will call exact. So let M be a D-exact category and let E be an exact category. Then we say that the functor from the D-exact category to the exact category is called exact. And note that here we want to define a notion of exactness where we have two categories somehow living in two different worlds. No? So M is a D-exact category, some notion from higher homological algebra, higher Auslander-Rayton theory. And E is an exact category, which is the kind of classical notion. So you couldn't really just naively say that F should preserve, for example, admissible D-exact sequences, because you don't know what an admissible D-exact sequence is in an exact category. We haven't at least defined it. But if you think about this for a bit, then you will probably come up with the same definition that I come up with here, namely that whenever you have an admissible D-exact sequence in M and you apply F, you get an exact sequence in E. So it's kind of a simple concept. An exact functor sends admissible D-exact sequences to exact sequences. So it turns out that the inclusion of a D-cluster tilting subcategory has a universal property with respect to these kind of functors. And that's why the ambient exact category is unique. So let me state that theorem, the universal property. So let's say we have a D-cluster tilting subcategory of E. E is weakly idempotent complete exact. Then first and foremost, the inclusion from M into E is exact. I would say this is basically immediate from the theorem of Hasso, where he, just based on how he describes the D-exact category M. If you have a D-cluster tilting subcategory, how it becomes a D-exact category is precisely telling you that this inclusion is exact. So this is maybe doesn't contain so much, and the second part is maybe what requires a bit of work, which is what I really do in the paper. So what I show is that whenever you have a weakly idempotent complete exact category, E prime, and an exact functor from our M to that weakly idempotent complete exact category, then you can find a functor which extends F. You can extend it along the inclusion to an exact functor from E to E prime, and the extension is unique up to isomorphism. So just to illustrate, in a diagram, you have your M, your D-cluster tilting subcategory of E, and you have your exact functor from M to some other exact category, which is weakly idempotent complete. And then what I'm saying is that there exists a unique extension, or an extension here, which is unique up to isomorphism. And this kind of universal property is what's telling us in particular that this ambient exact category containing M must be unique up to exact equivalence. Okay. So we've talked about uniqueness, but then the second part of my theorem involved the existence. So this is the next part. If you have a D-exact category, how do you show that it's equivalent to a D-cluster tilting subcategory? And this relies on the following notion, which plays a central role, which is the notion of D-extension closure. So here we have any full subcategory of an exact category, And we want to talk about what it means for it to be de-extension closed. So we say that U is de-extension closed if whenever you have an exact sequence, and now it's of length d plus 2, it has d plus 2 objects, d plus 1 morphisms, and whenever you have such an exact sequence where the outer terms are in your subcategory, then that sequence is Yoneda equivalent to an exact sequence where all your objects is in the subcategory. So this is a generalization of the classical notion of extension closure to higher D. Note that if you required these E1 to ED to be in U on the nose, then that would be too strong, because as long as D is greater than or equal to 2, whenever you have an exact sequence of this form, you could always just add a contractible complex of the form 0, E, identity E, 0, and add that to the middle here to ruin any kind of property of these things being contained in our subcategory. So somehow a better notion to work with, at least for us, is to require that the sequence is Yoneda equivalent to an exact sequence where everything is in U. As I mentioned, this generalizes normal extension closure, and that's just because if you have two short exact sequences, which are Yoneda equivalent, then the middle term has to be isomorphic. So in this case, E1 would have to be isomorphic to U1. So as long as U is at least close to an isomorphism, this would force E1 to be in the subcategory. So de-extension closure plays an important role in this kind of existence theorem. And this is a notion that already existed in the literature. I was not the one who introduced it. So I also rely on some previous work by other authors on the exact categories, in particular construction of the category of left exact functors. So first I recall what the left exact functor is, and here for simplicity I only need it when the codomain is abelian groups, but of course you could have a more general setting if you wanted. So a contravent functor is left exact if whenever you have an admissible d-exact sequence and you apply f to it, then you get the left exact sequence of the following form. So note that this sequence is obtained by applying f to the last term, to the second last term, and to the third last term, and then you ignore all the other terms in your admissible d-exact sequence. And what you require is when you apply f to these three terms, of course the arrows are reversed and you require this induced sequence to be left exact. Then we have the category of contravariant left exact functors, which we denote by Lm. And one can show that any representable functor is left exact, and that's basically just from the definition of the exact sequences. If you remember, we had some exactness when applying a contravariant home functor, and that exactness implies in particular that such a sequence is exact. So the Yoneda embedding induces a functor from M, a fully faithful functor from M to Lm. And then there are already some things which are known for Lm, and this is due to work by Ebrahimi together with Nasr Isfahani. And it's the following theorem. They show that whenever you have a d-exact category, then this category Lm is an abelian category, and the essential image of M into Lm is a d-rigid subcategory which is closed under d-extension. So here closure on d-extensions is this definition I gave on the previous page. And d-rigidity means just that whenever you have two representable functors, two functors in the essential image of this, then and you look at the X groups, then they vanish in all degrees between 0 and d. Of course, this would be obvious if you were looking at the category of all contravariant functors on M, because the representable functors are projective there. But we are not looking at the whole category of contravariant functors, we are only looking at Lm. This is a different abelian category with a different exact structure. And in this category, these representable functors are not projective in general. So this requires some work, and this is part of what they do in their paper. And for us, this is a very useful result, in which we will use to get the existence of a D-cluster tilting subcategory. just before, I just want to mention that d equals to 1 of their result tells us that the exact category is close to an extension in an abelian category. So it recovers the Quillen-Gabriel embedding theorem. So to conclude and get the d-cluster tilting subcategory, we have the following result. So note first maybe that this essential image of M is very close to being d-cluster tilting because it's d-rigid, but you somehow have no hope of generating or co-generating the whole of LM using M. LM is too big. So you need to find a smaller subcategory. And what I do in my work is to show that whenever you have an exact category and a weakly idempotent complete subcategory of it, which is d-rigid and d-extension closed, so basically satisfies the assumptions in this theorem they have, then you can find a unique extension closed subcategory of your exact category such that U, so now you have three things. You have U sitting inside F, sitting inside E, and what we say is that U should be a d-cluster tilting subcategory of F, and d-cluster tilting in such a way that the d-extensions in F are between objects in U are the same as the d-extensions in E between objects in U. In other words, the admissible d-exact sequences in U are precisely the ones which become exact when you look at them in E. So then you can combine these two results to get that any weakly idempotent complete d-exact category is equivalent to a d-cluster tilting subcategory. And yes, so that's all I had time to say, so let me stop there.
So thank you very much for your very nice talk. Thank you. And are there any questions or comments? So if not the case, maybe I just start with some naive question. In your first slides, you speak about the Frobenius exact enhancement of the classification subcategory. Can you a little explain about this?
Yes, maybe I can go back to it. Well, it might take a bit of time. So I think
no problem. Yeah, no problem.
Yeah. So I think, I mean, I'm just saying if you have a cluster category is a particular triangulated category. So what I mean is whenever you have a Frobenius exact category, you can take its stable category, the additive quotient by the projective injectives, and this gives you a triangulated category.
Yeah.
So yeah, what I'm saying by Frobenius exact enhancement of cluster category is just you have some Frobenius exact category whose stable category is equivalent to the cluster category as a triangulated category. And then since the cluster category has a two cluster tilting object, so this is in the stable setting, you can actually lift it to a two cluster tilting object in a non-stable setting in the Frobenius exact category itself. So that's what I mean.
Yeah. And is there a reference for this result? Or?
I don't know of a precise reference. There might be somewhere. I think it's a bit folklore. Yeah. Maybe Bernard knows better. So.
Oh, hi Bernard.
Hi.
Hi. Hello. Yeah. Thank you, Sondre, for the beautiful talk.
Thank you.
Yes, I mean you can construct cluster categories as Vertier localizations of algebraic triangulated categories, and therefore they're also algebraic.
Yeah.
Yes. So, for example, you can use yes. So in the hereditary case, you can also use the description as an orbit category. In that case, the fact that the category is triangulated was proved using the DG enhancement and hence the Frobenius enhancement.
Yeah.
And you can also, yes, for example, in the acyclic case, there's also a Hom finite exact Frobenius category, which was constructed by Geiss, Leclerc, Schröer. In general, of course, this category, this enhancement cannot be expected to be Hom finite, but in some cases one knows how to choose a Hom finite Frobenius model.
Yeah. So thank you very much. Are there any questions or comments?
Yeah, I don't know whether this is a question for Sondre or for Xiaofa. Is there a DG version? Is there a notion of the exact DG category? And are there analogous results in that framework? Would you expect that, or would you?
Maybe that's a question for Xiaofa.
Yeah,
I don't know.
DJ.
I assume I assume you can find them in nature as well. Yeah.
So that would be, you have some kind of D exact DG category, and then you realize it as D cluster tilting in some way.
Yeah, I don't know whether just the notion of D exact DJ category is already in the literature. I'm not sure.
Yeah, I don't know.
Yes, of course, and yeah, I mean, before that, one can ask similar questions about triangulated categories, but of course, or n-angulated categories, but of course, in that setting, a positive answer seems unlikely.
Yeah, I could say related to that, you can show as a consequence of this result, you can add some additional hypotheses and show that any Frobenius D exact category is D cluster tilting, D set cluster tilting, like close to necessities in a Frobenius exact category. That will be with a bit of extra work. You can add those adjectives,
yes.
Which I guess is kind of maybe closer related to the question.
It goes in that direction. Yes. Yes. Thank you.
So, are there any more questions or comments? So, if not the case, thank you, speaker, again. Thank you very much.
Yes. Thank you very much.